All right, so let's get started on the first section. Today we are going to have a brief overview of the memory technologies. This is the outline of today's lecture. First, we will use a concrete example, like the memory in a smartphone, to kick off our discussions. And then we will focus on a very important concept, memory hierarchy in the memory subsystem. And then we will talk about some array efficiency issue and chip examples. So first of all, for a VLSI system, don't forget about the memory. So if you look at the computer system today, we have three pillars to build up the system. You need the computation modules, like your processor, and then we need the memories to store the data, and then you need the communication channels to fetch the data from the memory to the computation units, and then save the data back. So you need those three components. And here we are going to focus on the memory because it's becoming more and more important in the whole system as we are entering this big data era. All right, so let's have a teardown analysis of a smartphone. And you are using those kind of smartphone in your daily life. And here we use an example from Samsung S20 Ultra. So this is the smartphone, and we want to tear down it. So here we are citing the analysis from the Tech Insights, which is a company specialized in the reverse engineering. So if you take off the screen and then look at the circuit board underneath, so this is how it looks like. And so here we have multiple chips packaged on the and then assembled on the circuit board. Of course, there are many more discrete components, but here you see those big chips here. And I don't know if you can read those small text, but basically here for this one, here, this big chip is your storage. It's a 256 gigabyte NAND flash, and it's made by Samsung. So this is your storage. And then here this chip, it says here, it's your processor and the DRAM to package it together. So in this chip, actually in this package, I would say, you have two chips packaged together. So those two chips, one is your processor, in this case, Qualcomm Snapdragon 865. And then it's co-packaged with Samsung DRAM. In this case, it's a 12 gigabyte LPDDR5 DRAM. And we will discuss what is LPDDR later in the DRAM lecture. It's one of the interface, I/O interface protocol. So in this case, you see that the DRAM is close with the processor. So then they are co-packaged. And then you have the NAND here. Of course, you have many other components on the circuit board. For example, the power management, Wi-Fi for your LTE, 5G modules. So those are separate chips on the circuit board. So this is the back side of the board. I will not go into the details. So here, mostly for the power management and the wireless communication. So the biggest chip, as you see, is this NAND flash and the processor plus DRAM. All right, so here let's take a look at the cost breakdown. So here in total, this phone cost is around $528. Of course, Samsung sells at higher price. No, this is probably like 1,000. But the cost is about like 500. So here is a breakdown of the cost, and you see so many modules in the smartphone. And here we highlight the memory contribution. About 1/8 cost is for the memory. Of course, the memory here we have the DRAM and the NAND flash. So two components. And then the other big cost contributor will be the display, the OLED, the organic LED, and the camera. Of course, you have like 3 or 4 cameras on those high-end smartphone. And finally is the CPU plus GPU, the processor. So here you see that roughly those 4 are the top 4 contributors to the system cost. Of course, you may have some other modules like sensor and power management and wireless communication, and then assembly test. So this is the breakdown to give you some intuitive understanding of the system. So any questions here? If no, then let's move forward to the memory hierarchy. So let me check if any questions from the online. So for the online audience, if you have questions, please post to the chat. I will check that regularly. But of course, I have to prioritize the audience in the classroom first. Okay, memory hierarchy, very important concept. We are going to use this concept through the class. I mean, for this whole semester, we are going to use the memory hierarchy to guide our discussions of different components of the memory system. So first of all, let's look at this Moore's law, and I believe that many of you are familiar with this. So here basically the Moore's law says that the transistor count on the chip, so here transistor per die, exponentially increases over the years. And here we show different chips, and then you see this is indeed an exponential increase over the past 50 years. But here you will see a slight deviation from the historical trend. So here let's say the red ones, so those are the Intel CPU for both like your PC and server. Of course, this has a long history starting from like 1970s. And at that time, the system also has the DRAM. So you will see those. These red ones are the PC. And then the black ones are the DRAM. So then as we approach like in the past decade, you see that here those blue ones, the NAND flash, take off. So the density of the NAND flash really outpaces other technologies. So, and you see that also the transistor count on the CPU, and also GPU and Apple's mobile CPU. So they are about like a billion to, so here 10 to the power 9, is a billion. So it's about 10 billion, 1 billion to 10 billion range transistor count on the chip. This applies to all kinds of CPU and GPU. And also DRAM is a little higher than that, I believe. So the highest density is the NAND flash. That's why you have like tera. So this is really more than the transistor count in the CPU. So roughly there's like 10x gap between the transistor count in the memory and this memory, in this case, the NAND flash, which has the highest density among all the technologies. And also you see the slow down of the transistor count in the CPU. As you know, the Moore's law tends to slow down in the recent years because we are approaching the scaling limit imposed by the physics. We will discuss some of those challenges in the later lectures. But this is like an overview of the growth of those transistor counts on a chip. This is on a single chip. A single chip is called a die. Of course, you can stack multiple chips in the system through advanced packaging. Then you can still realize more functionality in the system. So any questions? All right, then let's look at the memory hierarchy. So this pyramid structure basically talks about the trade-offs in the memory characteristics between the latency and the capacity. So latency means how fast you can read or write the data from those memory devices. Capacity, of course, how many bits you can pack on the single chip of those memory. So here, this pyramid from the top, starting from your processor core. So the processor core does the logic functions, like your ALU, arithmetic logic unit. So this is how you perform your logic and numerical functions there. But then the core needs to take the data from the memory. So the first level, it will take the data from the L1 cache, and then we will have L2 cache and L3 cache. Sometimes we may have the last level cache. So those caches basically are the memories on chip, or they are also called embedded memories because they are on the same chip with the processor. So here we see this like this box, this yellow box. So the technologies that are on the yellow box are on the same chip with your ALU, the logic functions. And mostly here we are using like SRAM, static random access memory, for the on-chip caches. And then you can have different levels of the caches. We'll discuss what are the differences in the design later. But as we move along the hierarchy vertically, you see that the latency changes. For example, here the L1 cache typically can operate below nanosecond. This essentially is the same as your clock frequency. For example, if you are like 2 gigahertz, then your clock is about 0.5 nanosecond. Then that means you can read and write your data about 0.5 nanosecond from the L1 cache. But as you move down the hierarchy, then the last level cache, probably the latency will reach to like 10 nanoseconds. So it will be slower. But at the same time, you see that the capacity increases. So the L1 cache typically tens of kilobytes, and then L2 cache like hundreds of kilobytes to megabytes, and then the L3 cache a few megabytes to tens of megabytes. So there's a trade-off between the latency and the capacity. And then this is on-chip memories, and then off-chip. So the first off-chip memory will be this main memory, and this is made by the DRAM, dynamic random access memory, and you probably see this kind of DRAM on the DIMM, the DIMM. This is called DIMM, Dual Inline Memory Module. So you have this DIMM, and you can insert that to the motherboard of your system. So those are the DRAM chips, and DRAM, the latency is about tens of nanoseconds, like 30, 40 nanoseconds. And the capacity of DRAM today, you can look at the specs of your processor, right? So it's about 8 gigabytes, 16 gigabytes, and so on. And here we have a boundary in the hierarchy. You see that this red line. So here above this boundary, like your SRAM and DRAM, are called volatile memory. So volatile means the data will be gone or will be removed after the power supply is removed. So you cannot store your data forever there. So once you remove the power supply, then your data is gone. You lose your data, you lose your information. And then below this line, then we have the non-volatile memory. That is for storage. Then you can keep your data for a longer term. And then here we see the solid state drive, SSD. This is enabled by the NAND flash technology. And the latency for the NAND flash, like read to write, is about like 10 microseconds to hundreds of microseconds. So it's much slower than the like DRAM or the SRAM. But you can carry more bits on the flash. That's why how you store your video, your images on your SSD. So you can have like hundreds gigabytes, 256 gigabytes, 512, or even today like 1 terabyte SSD. And then at the very bottom of the hierarchy, then we may still have the hard disk drive, especially in the data center like large scale system. Then because you can have like tens of terabytes, you can save your large amount of data on this one. But the latency is pretty long, like milliseconds. So this is basically the trade-off between the latency and capacity in different technologies. The idea here is that, let's say, ideally, you want both fast memory and large capacity memory, but fundamentally, you cannot achieve that simultaneously. That's why you have to break that into this hierarchy to have a trade-off. Either you have fast latency or you have large capacity. It's really difficult to achieve both at the same time. So here, any questions? Okay, one more thing here. For those level in between the SSD and the main memory, here we have this so-called storage class memory. This is something that is emerging. It's not widely used in today's system, but we're going to discuss some of the new technologies to enable this storage class memory. And you may find some products, for example, from Intel. They are selling this so-called Optane high-end SSD as this storage class memory. So this is something emerging. And also the last level cache Sometimes if you find the IBM's like a server processor, it will have like EDRAM, embedded DRAM, as a last level cache. So we will talk about those in later lectures. Let's say if I have any questions online. For example, you can also look at the those memory specs for your laptop. So, for example, for my laptop, this was purchased like 3 or 4 years ago. So here, this is Intel i7, nominal clock frequency like 1.9 gigahertz. And here you see that it has a cache hierarchy here, down to here. L1 cache in this case, 256 kilobytes, L2 1 megabyte, L3 8 megabytes. And this is on-chip memory, so that's why it's shown under the CPU. And here the memory really means the DRAM, the main memory of the system. And in my case, I have, I believe, 16 gigabytes DRAM in this case. And then disk here really means the SSD. This is a Samsung SSD series number here. And it's 512 gigabytes. So this is in my system. All right, any questions before we move on? So this memory hierarchy is very important. This will be our guideline to discuss individual components later. So here we show like a image for a processor, and we will take a look at that in later slides in more details. So we will look at where is the cache on this processor. So here I quote a professor from Stanford. He says that 21st century workloads is all about data, especially large amount of the loosely structured data. So those loosely structured data, like your streaming video, audio, natural languages, real-time sensors, contextual environment, you take the data from the environment, basically. And we are gathering the data at very fast rate every day. Like you take your images, upload the video to, like what I'm doing right now, right? So I'm recording the lectures. Later I will post the lectures to the YouTube. So we are creating a lot of data these days. Big data means big memory. So you need the memory technologies to host those data, and also you need to process the data, fetch the data and process the data. And here just some examples. The deep learning, as you know, is very powerful and popular today. And the deep learning, the enablers, I would say, of the deep learning. If you look at the history, right, like the algorithm was actually invented in 1980s by Yana Kun as the SGD, stochastic gradient descent, for the backpropagation. So in 1980s, the algorithm was already invented, and it was applied to the MNIST dataset, the handwritten digit recognition. But you can only do that simple task at 1980s. So the real enablers for the deep learning today, two factors. One is the amount of data we gathered. So this creates the training data set for the learning. So you need to gather a lot of images. For example, in this image classification problem, then you have to gather those images as a training data set to teach the network to learn those patterns, learn those features. So then this is only possible with a large amount of data. And second is the computation power, especially enabled by the GPU. Without the GPU, it will take forever to train those data sets. But even with the GPU, for example, here you see that to train 10 million, that's 200 by 200 pixel images, it takes 16,000 CPU cores plus 1,000 GPU as a cluster, and spend the next 3 days to train the deep neural network. So this is a really computational resource demanding in terms of the computation and memory capacity of the system. So here, to meet the demand of those requirements, companies are trying to specialize the hardware to do those training or the inferencing workloads. So here is an example from Google, Tensor Processing Unit, TPU, and we'll briefly talk about that at the end of the semester. So this is a domain-specific architecture to process the data in the tensor format. Tensor, is a matrix and matrix, or like a multiplication. So here, Google is building the custom chips, and it was assembled to the data center infrastructure, like building a cluster of those TPUs. In this case, burning like hundreds of kilowatts to train the algorithms behind the AlphaGo. So this is a trend in the industry, and the software companies are hiring hardware designers. And actually myself, our group is working with Google to develop some of the in-memory computing technologies. So software companies are hiring hardware designers, and not only Google, and I have friends in Facebook, in Microsoft, in Amazon, and you see the news, Tesla, right? So they're building the custom chips. So here, we're going to address one issue, the memory wall problem in the memory hierarchy. So if you look at the hierarchy from the on-chip, like CPU and cache performance, versus the main memory performance, the DRAM performance, there is an ever-increasing gap in the performance. So here I took this chart from this famous book from the Stanford president, ex-president, John Hennessy. So this is like a Bible for the computer architecture book. So it shows the normalized performance of the processor on-chip performance versus the bandwidth that the DRAM memory can provide. Over the years, you see that there is a ever-increasing gap. So that means the processor can run very fast, but you don't have enough data, or let's say you don't have enough time or bandwidth to fetch the data for the processor to compute. So the bottleneck of the system will be the bandwidth of the memory DRAM performance. So let's take a look at the DRAM. So here, this is a trend of the DRAM in terms of, on the right-hand side, this is let's say, DRAM DIMM capacity in terms of, for example, the gigabyte. And then here, we have the number of cores, the CPU cores. So today's multi-core system. So the number of cores increases, or let's say doubles, almost every 2 years. This is for like server kind of platform. But the DRAM capacity doubles every 3 years. So that means the number of cores outpace the DRAM capacity. So the system can run very fast, but you don't have enough bandwidth to provide the data. So this creates the memory wall problem in the memory hierarchy. And also from the energy perspective, you will see that today's applications are consuming most of the energy in the memory access. So here I quote an analysis from Professor Mitra, Stanford. So here, this is some natural language processing workloads or the genomics, like the gene sequencing applications. So it analyzes the energy spent on the compute on your CPU cores versus the energy spent on the DRAM memory access through the data bus. You fetch the data from the DRAM. So you can see that here, most of the energy spent on the memory access. So in this case, their system has 2 CPU. Each CPU is 8 cores, and the system has 128 gigabyte DRAM. So most of the data is spent on the DRAM access instead of the processor. So from the system perspective, so the memory is a bottleneck of today's system in terms of the energy efficiency. Any questions so far? Not only the gap exists between the CPU and the DRAM, but also there's a gap between the DRAM and the NAND flash. So here I quote this from actually almost 80 years ago, this analysis between the memory. So in this case, it's really the DRAM versus the NAND flash. The cost per bit. So this, of course, is at that time. So DRAM, if you normalize the cost per gigabyte, you need like $5.5. The NAND really cheap, like 70 cents per gigabyte. But the latency-wise, DRAM like tens of nanoseconds, NAND is like tens to hundreds microseconds. So you have like 1,000x difference between the speed. And then here there are some other metrics. For example, endurance and retention. We'll talk about that later in more details. Endurance is a metric to evaluate how many cycles you can read or write the memory bits. And DRAM is theoretically infinity, has endurance approach infinity. In this case, like 10 to the power 15 cycles. But the NAND flash, as we learn later, has a very limited lifetime. You can only write the data into your NAND flash about like 10 to the power 4 cycles. That's about 10,000 cycles. After that, that NAND flash cell basically is dead. You cannot use it anymore. So we will discuss the details why this happens later. There's a difference in the cell endurance. And also data retention. So the DRAM, as we know, is volatile memory. That means if you remove the power supply, then your data is gone. But NAND flash, you can retain your data like 3 months to 10 years. So there's big difference. And also the bandwidth power has a very different characteristic between DRAM and flash. So here, the point is that there is a gap between DRAM and flash in terms of those metrics here. This opened the opportunities for emerging memories because we see those gaps. If we can invent a new technology to fill in those gaps, then you can make the whole system's performance more balanced. Right? As long as you increase more levels, introduce more levels in the memory hierarchy, then you will have more balanced and smooth performance of the whole system. There will be no bottleneck, basically. Then the question is which memory for which application? There are so many emerging technologies out there under the research and development. Then the question is which memory for which application? So here let's use this chart to discuss the opportunities for emerging memories. And here we show the trade-off between the latency, access time in terms of seconds, versus the density. This is a bit per millimeter square. So think about 1 millimeter square silicon area, how many bits you can pack into that 1 millimeter square. So here we have this mainstream technology today, like SRAM is in this corner. Why? Because the speed here is like nanosecond, and then the density, 1 millimeter square, you can only have like 10 to the power 7 memory bits in SRAM. And then we can have the DRAM here, and then NAND flash is here. It's very slow, as we see here, like this is tens of microseconds, but the density can approach like 10 to the power 10 bits per millimeter square. So we see a big gap between those like DRAM and NAND flash. So if we can improve the NAND flash and DRAM performance, then what would be the trend? So today, of course, the memory industry is still improving the DRAM and the NAND performance, not necessarily performance, I would say the density, by 3D integration. So you can have DRAM or NAND flash stacked vertically. So on the same 2D footprint, like 1 millimeter square, you can have more bits packed together because you are utilizing the 3D, the third dimension, the 3D integration. So in this, with the 3D, then the density is increasing, and so that's why you see the trend moving towards the right. The density is increasing, but not necessarily the performance. Like the speed is still roughly stays the same. 3D, because the 3D only helps with the integration density. You can have more bits, but not necessarily each bit can be accessed faster. Then here this gap, as we showed earlier, introduce this concept, storage class memory. And there are many candidates for this one. So one notable example is this 3D exponent technology made of the phase change memory. So this was commercialized by Intel and Micron back in 2016. And you can find those products online. I mean, in the market, you can buy it. I think a few $100 for the Optane SSD. So this really addresses the gaps between the NAND flash and DRAM. And also for the gap between the SRAM and DRAM, the idea is to introduce some last level cache made of some emerging technologies. Of course, like IBM has the EDRAM, embedded DRAM, but we see opportunities for other emerging technologies like the STT-MRAM, the magnetic random access memory, and also the ferroelectric devices. So they may play a role in the future system for those new technologies. But of course, those new technologies are still under the research and development. But the industry is investing a lot on those new technologies these days. Any questions so far? All right, then let's, yes, please. So that's a good question. So I would say for the memory system, if you stack in 3D, like 3D NAND, as we discuss the details later, it won't help too much with your latency. So because NAND still has a non-strain with those transistors, the precision RC is still large. The LAN strain, I mean, in the 2D case, it's a non-horizontal LAN, horizontally, and when you stack into 3D, then it's still a long LAN in the 3D dimension. So the NAND speed will not improve too much, and the DRAM is a different story. DRAM is like multiple dies on the 3D. So the DRAM, the speed will not increase too much, but the bandwidth can increase because you can have more like pins with the DRAM I/O. So we'll discuss some more details later. But DRAM, I would say the speed will not increase, but the bandwidth can increase. Yeah, so that's a very good question. So I would encourage those kind of discussions in class. And we will discuss those more details later. Today is just an overview of the technology. All right, so the last topic today is array efficiency and the chip examples. So here, this is a generic memory array architecture. So no matter which memory technology you are talking about, it has a generic organization like this. So we will have in this case, is a 2D array. We'll talk about 3D array later. So in the 2D array, so you have this word length horizontally for the rows, and then the bit length vertically for the columns. So the intersection of the word length and the bit length will be the memory cell, and this memory cell can be SRAM, can be DRAM, or can be flash. And then this is a cell array. So this basically this matrix is a 2D matrix, the rows and columns, and each cross section is a memory cell. And then the peripheral circuits, typically you have the row decoder. So this is the row address, like m bits. Then you need to decode that into 2 to the power n rows. So here are the rows, you have 2 to the power m rows, 2 to the power m rows. So for example, like 10 bits row address, you will translate that to 1024 rows. And then the column-wise, you will have this column decoder. So the column decoder plus the mux. So column decoder will select which column. So let's say row address, you will select which row to access. And then column decoder will also select which column you want to select. And after that, we may need the mux, because here, from the column side, you will have 2 to the power n column groups, and each group, here we don't have the bit selection. So let's put it this way. So from the column side, for example, you can have 4 if k equals to, let's say, 8. This is as one group, because 8 bits, is 1 byte. So if your like I/O is just 1 byte, you will select a group of columns, in this case k bits, as one group. So every time you are going to transfer the data in 1 byte, 8-bit fashion. So in this case, the number of columns will be k times 2 to the power n. Why is that? Because from the n-bit address, you will decode 2 to the power n groups. And each group, you will have 8 bits. Within the group, you don't have the selection, because every time you are going to read out 8 bits together. So in total, you have k times 2 to the power n columns. And then through this mux, you only get this k bit out. In this example, only 8 bit out. So this 8 bits will be sensed by the sense amplifier. Because normally when we read out the signals from the memory array, it's a small signal, like your voltage or current, but you need to sense that and amplify that to the digital 1 and 0. So then this I/O is like k bits in this case. So any questions on this generic array? Of course, for different technologies, we may adapt this a little bit, but overall, this applies to all kinds of memories. All right, then let's talk about the memory cell. So the memory cell area is usually measured in the number of f squared. So f, you can think is the minimal feature size of a certain technology node, like for example 20 nanometer. So here we show some of the typical values for the area per bit. For example, for the SRAM, we will discuss that later. SRAM is a 6-transistor design. And if you lay out that into the silicon, then typically you have like 7 to 10 F for the height of the SRAM cell, and 20 to 30 F for the width of the SRAM cell. So in total, you will have like 150 F squared to 300 F squared in terms of SRAM and area, cell area. And the SRAM depends on the L1 to L3 cache. Then this number may vary because L3 we have to L1 we have to size up the transistor W over L, the width over the length. Therefore, you have to use larger transistor. Then you may have like 300 F squared. But it's pretty big. And then DRAM, 6 F squared. DRAM we will see later is a 1 transistor, 1 capacitor cell. And when you lay out that, it will probably like 3F by 2F. So you will have 6F squared. It's much smaller than the SRAM, as you see here. And then for the NAND flash, so here the NAND flash is a single transistor. It's a floating gate transistor. And it can have very minimal spacing, like 2F by 2F. We'll discuss in more details later. But here you just need to know that the 2-dimensional 2D NAND flash, 1 floating gate transistor occupies 4 F squared silicon space. And F can be, for example, 20 nanometer. If you normalize to 20 nanometer load, then it will be 20 nanometer by 20 nanometer by 4. But this is the cell area. For the flash, we will talk about later. Flash can have this multi-level cell operation. So what is that? That is for one memory cell, here 1 floating gate transistor, you can store more than 1 bit data. For SRAM, DRAM, it's 1 bit data. You can have only 1 and 0. But for the flash, because we want high density, large capacity, therefore we can have multi-bits per cell. So that means, for example, 2-bit data. That means you can store 0, 0, 0, 1, 1, 0, 1, 1 in 1 floating gate transistor. We'll talk about how to realize that later. But here, conceptually, you can think you can have 2 bits per cell. So if you have 2 bits per cell, then each bit will take equivalently 4F squared divided by 2, right? So divided by the number of bits in one cell. And more aggressively, you can do 3 bits per cell. Then each bit equivalently will take 4F squared by 3. And today's NAND flash, you can even find 4 bits per cell. So that will be 4F squared by 4. That is for 1 bit. This is for bit area, equivalent area for 1 bit. So you need to divide it by this n bit number here. And then today's NAND flash, as we introduced earlier, has already adopted the 3D integration. So that means one string of the NAND this is like your pull down network of your logic. That's why this is called NAND. you have a series of those floating gates. And right now, those floating gate transistors are standing up vertically on the chip. So then the equivalent area is to divide by the number of layers. So here on the 2D space, like your XY plane, you only take like 2F by 2F silicon space, but you are stacking like transistors vertically. So each transistor you will have equivalent area like for F squared divided by L. L is the number of layers, and then you multiply divided by N, the number of bits. So then this can be very small, right? The equivalent bit area will be very small because today's L, if you look at the specs from like Micron, SK Hynix, it's 176. You can have more than 100 layers in the 3D dimension. So then this area is so small. So even at the same technology load, like the same F, you will see that SRAM will be like tens of thousands higher, let's say, equivalent area than the flash. So that's why flash becomes so cheap these days, because you can pack so many bits within this 2F by 2F silicon space. So any questions here? So what's the question? 4F squared divided by N divided by L. L is the number of layers. What's your question? N equals to L, I mean? So I didn't get your question.
So equation wise, so for the 2D NAND flash, the effective area per bit becomes 4F square upon N, right?
Yes.
Because it can store a large number of bits per.
Yeah. Yes.
So if we increase the number of layers vertically,
yes,
then it should effectively be F square upon NL, right?
Yeah, so that's why here is 4. If you also consider the multi-bit per cell is 4F squared divided by N, and then if you have L layers, then divide by L. Right? Is this clear? So this is from the MLC, the multi-bit per cell, and then this L is from 3D. So then you will have two mechanisms to reduce the equivalent area per bit. One is through the number of layers, the other is through the multi-bit per cell. All right, so I think let's have one last slide before we end today's lecture. So here, another concept is the memory array efficiency. So by definition here, this array efficiency is defined by the area percentage occupied by the memory cell over the memory cell plus its peripheral circuits. So what does this mean? For example, let's take a look at this. This is a NAND chip, NAND flash chip. So you see that here, those parts are all the NAND flash memory cells. And it takes most of the area. But you see some yellow modules here in the middle and also on the side. This is like row decoder, and then this is like a bit NAND, like a sense amp, and those peripheral circuits. So the array efficiency is defined as the NAND flash, the cell area, divided by the total chip area. In this case, for the NAND, typically like 70% or 80% of the area is taken by the NAND flash cells. And an additional like this 20% or 30% taken by the peripheral circuits. The peripheral circuits, as we discussed earlier, may have the address decoder, sense amplifier, control logic for the timing, I/O, and also for the NAND flash, we need to create high voltage, like those charge pump circuits. So, but most of the area spent on the memory cell. So this is what you wish, because those peripheral circuits will not increase your capacity of the chip. The memory cell array is the bits. It's all about your bits. Then the other circuits is just to provide the assistance to the chip. So here we wish to have a high array efficiency. And then for the processor, on the right-hand side, we have a CPU. And in the processor, here we see that this part is L3 cache. Here, when we talk about the array efficiency for the L3 cache, it's not this red box divided by the total chip area. We are talking about this L3 cache. Within the L3, you see that there's some different colors here. So probably this part is like the SRAM area. And here, this part is about the peripheral circuits. So when we talk about L3 array efficiency, we're talking about this SRAM area. Oops. This SRAM area divided by the total L3 area. We're not talking about the total like chip area, because in the chip you have like a CPU cores and I/O. So here when we talk about L3 array efficiency, we're talking about the within the L3, how much is taken by the SRAM cell, how much is taken by the peripheral circuits. So this is a difference than the NAND flash, because in the NAND flash array, you will only have the memory and the peripheral circuits. But on the CPU, not only the L3 cache, you have other modules like the ALU and other logic functions. So this is some slight difference between the definitions for the off-chip versus on-chip memories. For on-chip memory, we have to specify the memory component first, and then within the memory component, then we talk about how much is taken by memory, how much is taken by peripheral circuits. And normally for the processor like caches, the array efficiency will be low, like 30 to 50%. And for the standalone like DRAM and NAND flash, it can be high, like 60, 70, even 80%. So any questions before we stop here? Yes? No, for the whole CPU, we don't define that because you have the logic functions. We talk about the array efficiency for the memory component only. All right, so then let's stop it here today.